Swayam Prabha. Digital India. Educated India.
Hello all. So welcome to Astrochemistry. This is lecture 21. Now, before looking into what we shall be studying in this class, I'll give you a brief recap of what we saw in the last few lectures. Now, in the last 2 or 3 lectures, we looked at how molecules and atoms may be detected in space. We started off by looking at how we can understand what the sun is composed of. This happened approximately 200 years ago, right? We're talking about the 1800s, Now, or 200 to 150 years ago, approximately in that time. So we saw that molecules could be detected in space by overall obtaining light from a star. For example, you obtain the radiation from sun, for example, okay? That is how you start with. So you obtain light from a star and you look at its spectrum. Now, what is a spectrum? A spectrum, as the way we understand it in our class currently, is simply a list of energies of various electromagnetic radiations. All right. So we obtain light from a star and then we looked at its spectrum and we compare the spectrum of known species available on Earth. And then once we make a comparison, if the spectra match, we understand that what is present in that celestial object is the same species that is present on Earth. And that's how we happen to know that the sun consists of the same elements present on Earth. All right. So this was the brief overview. And now the idea that we can detect molecules, and atoms in space by comparing the spectrum led us to understanding and looking at the various wavelength ranges. And I had given you as homework to find out the corresponding frequency and energy ranges of various electromagnetic radiations. You may just go back to the previous lecture and find the specific homework I'm talking about. So this is where we stopped at. So now, having understood that, we need to ascertain and explain clearly how light interacts with matter. Okay, right? So it is by analyzing light obtained from star, which contains matter over there. Okay, right? Which contains matter over there, that we can eventually identify all the molecules and atoms present in space. This is the broad picture overall. Okay. So today, with this understanding, we shall look at what all could happen to the molecules or atoms, right, which give rise to these spectral signals. Do you understand? I mean, why should molecules and atoms give rise to various spectral signals? Even though I haven't clearly and precisely defined the word, this phrase spectral signal, without even defining that clearly, for now, please take it that we're just talking about some kind of a signal obtained from the molecules, okay, from the molecules, which corresponds to, in one way or the other, a list of energies corresponding to the various wavelengths in the electromagnetic radiations. A more precise understanding will follow soon in subsequent lectures. All right, yeah. So the question is clear. Why and what all could happen to molecules, that lead to these spectral signals? That is what we're going to be understanding today. And today we'll be beginning to look into this aspect. In the future classes, we shall expand upon this area. So with this introduction, I will go straight into the content for today. So what all could molecules and atoms do? What do you think they can do? Forget molecules and atoms. What all could you do? Well, when I say what all could you do, what are the ways in which you could move about? Eventually, one kind of gets an intuitive understanding that it's the ways in which, the various ways through which molecules move about that lead to the various spectral signals, right? If a molecule does nothing, if a molecule were to simply, just be itself, why should it interact with light and give a signal? The understanding is that a molecule or an atom right, as it interacts with light. Undergoes various types of motion. Now notice that I have used the phrase a molecule or an atom. The same idea is also applicable to a bunch of molecules and atoms. But to begin with, to keep the discussion simple, let's first understand what happens to one molecule, and then subsequently we'll understand what happens to a bunch of them put together. All right? Yeah. So, I mean, before we proceed further, why should when a molecule of an atom interact with light, right? Why should it even undergo any type of motion? Why can't it just stay still? What is the quick answer? A quick one-liner to answer this question. The answer would be that. Well, as a molecule of an atom interacts with light, what is light? Light is a source of energy, right? Light gives you some source of energy. So light is a source of energy. And once this external energy, right? Once a molecule gets this external energy, it doesn't stay in its own state, right? Based on simple Newton's classical laws of motion, right? Once this external energy, right? Once the external energy interacts with the molecule, right? The molecule, then the molecule begins to move in various ways, right? So once the source of energy is given to a molecule moves. Now I use this phrase move, right, in a very colloquial way. I haven't defined what move is. I've used it like a lay person, right, without any proper understanding of physics or chemistry. And I'm simply saying that a molecule will move, right? A molecule will move. You would assume that it would be based on the laws of classical mechanics, or in this case for a molecule, actually it's quantum mechanics. However, the broad idea is that it still moves, okay? A molecule still moves, and it is now important for us to discuss the various types, okay, right? Various types moves through various ways. So this molecule actually moves in various ways, and these various ways via which a molecule moves, right? By moving, I'm not simply talking about, going from one point to another. I'm just talking about all kinds of motion associated with the movement of an atom or a molecule. All right. So all of these together, right, they result in the spectral signals obtained. So before we proceed to see how the spectral signals are obtained, right, we shall look at the various modes of motion, for any molecule or atom. Okay. So the modes of motion for a molecule. Now, an atom is nothing but a subset of a molecule. So, because what is a molecule made up of? Many atoms, right? So once we understand the molecule, I will specifically, talk to you about the atoms very soon. All right. So for now, we're going to be starting by understanding the various modes of motion of a molecule. What do you think? Based on your intuition, what do you think are the different ways in which a molecule could move about? Well, one, it could simply move from one point to another via what is called as a translational motion. What's a translational motion? Well, one is what is translational motion? That's the most common type of motion we all undergo also, right? We move from point A to point B, We move from point A to point B. As part of this translational motion, what happens is that our Cartesian coordinates change, right? Our XYZ Cartesian coordinates change as part of translational motion, and this process, is associated with some kind of a linear momentum. All right, So this is what is translational motion. This is simply going from point A to point B. That's our colloquial understanding. Okay, right? So translational motion, is understood as the motion where one, the Cartesian coordinates of the system of the molecule changes and is associated with a linear momentum whose magnitude is given by m mod v, right? So the magnitude of this linear momentum is given by m mod v. Are we good? So this is what is called as translational motion. What are the other types of motion which a molecule could undergo? Well, I mean, this must have been familiar to you folks from high school also, correct? Or in collegiate thermodynamics in physics or chemistry. What are the other types of motion? Yes, the next type of motion is what is called as rotational motion. B. So what is this rotational motion? Well, again, right, to understand what happens to molecules, let's think about ourselves. What does it mean when we rotate? We rotate, what does it mean when we actually rotate? How do you try to understand rotation? Rotation typically refers to movement about an axis, correct? So by rotation, I'm talking about movement about some arbitrary axis. And what is this axis? What is an axis itself? An axis is nothing but some imaginary line about which the motion happens. Okay, right? And a key point to note is that in rotational motion, right? When it is rotational motion alone that's happening, right? When it is rotational motion alone that's happening, in pure rotational motion, the Cartesian coordinates, of any molecule does not change. It should not, right? I mean, when I'm doing this, and I have rotated, my Cartesian coordinate did not change, right? If I'm only talking about like rotational motion, the Cartesian coordinates should not change. Okay, right? But notice the point. I have used the word pure rotational motion. This is only when I'm only undergoing rotation. But rotation can also be coupled with translation, right? What is an example you could think of? The Earth orbiting around the sun, right? When the Earth is orbiting, the Earth rotates and it's also undergoing some translational motion also, right? Do you understand? Its coordinates also change along with also rotating. Okay, so when we're talking about a pure rotational motion, the Cartesian coordinate of the molecule does not change. The Cartesian coords. When I say the Cartesian coordinates of the molecule, you could probably think about the center of mass or one specific point. Okay, right? The Cartesian coordinates of the molecule do not change. All right. So this is the other point. What's the third important point associated with rotational motion? If in translational motion, you have some kind of a linear momentum always, getting transferred. I mean, from the system to the surroundings and vice versa, etc., etc. In rotational motion, what's always involved? Some kind of an angular momentum is involved, right? Okay, right? So I'll just keep it here. Angular momentum, right? The vector L, okay, right? Is always associated with rotational motion. Angular momentum is involved. So this is our understanding of rotational motion. What else? Could happen to a molecule? Can you guess? So we've discussed about translational motion. Next, we've discussed about rotational motion. The other kind of motion that a molecule could undergo is, what is this? Vibrational motion, correct. Okay, right? So another thing that can happen to a molecule is what is called as vibrational motion. Now, what are vibrations? See, in all our study of the translational, rotational, vibrational motion, etc., we don't care about the precise definitions. We just want to understand, in a working way, to have a working knowledge of what translation motion is, what translational, rotational, and vibrational motion, etc., are. Okay, we're not specifically concerned with the proper bookish definition. We don't care about the book definition, but rather, I want you folks to have an intuitive understanding of what these different types of motions involve. Okay, yeah. Okay, so what is vibrational motion? Well, vibrational motion, the minute we think of vibrational motion, what comes to your mind? Think about like high school physics. We think about simple harmonic motion, right? Simple harmonic motion. Or else, for example, even if you have, if a person has a very high fever, the person shakes. What's the characteristic of that shaking? The person does not shake from one position to go to another position, right? The person's body shakes such that it comes back to its equilibrium limit, right? This coming back is the key to vibrational motion. So overall, it could be understood as, right, a motion, more specifically, some sort of a to and fro motion about a specific point, right? What do we always think of vibrational motion? It's like tuck, 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 right? So the key thing is to and fro. You have motion going away from a point, and the motion has to be restored back to the same point. Okay, and yet another feature of the vibrational motion is that is always associated with some kind of a restoring force. Now, why is it called as a restoring force? Because the force that restores the motion, right? If it's going in one direction, it has to be restored to another direction. That's why it's called as a restoring force. And the force, okay, right? And force is in the opposite direction of the displacement. Okay, that's the key with vibrational motion. Is in the opposite direction of displacement. Are we clear? Okay, right? So, so we have like three types of motions as far as molecules are concerned, right? We have what are called as translational motions, rotational motions, and vibrational motions. And notice again that the key idea is that, typically all of these three things can also happen together. That is, at any given time, a molecule could always undergo translational, rotational, and vibrational motion at once. Okay, right? Now, these understandings of the types of motions are for purely for vibrational motion, this is valid. So purely for rotational motion, this is valid, etc., etc. But when all of these, when all three things happen together, all of them occur. Okay, right? For example, if you're talking about vibrational motion, right? Vibrational motion could always be accompanied with rotational motion and translational motion. Okay, and in fact, they do happen in the case of molecules, as we shall specifically look into some examples very soon. However, as isolated pure concepts, right? There are key distinctions between the types of motions, and they have been listed on the board here. So these are the different types of motion. Now, when it comes to molecules, they also undergo a very special, yet another form of motion. This is not exactly, you can't call it a motion, but it's a state change. It's a type of change that is called as change of electronic state. Okay, right? I will first go through all of this, and I'll come back to the electronic state towards the end of this lecture, approximately. Okay, so please understand, as far as molecules are concerned, what are the different types of motion? Translational, rotational, and vibrational. On top of this, molecules or atoms can also undergo a change in the electronic state, right? Which strictly cannot be called a motion, right? Yeah, but nonetheless, that is also part of the reason why molecules give rise to spectral signals. And I will talk about the electronic change of state very soon. Okay. Now, having understood the different types of motions, our next task would be to try to understand and kind of quantify, how these motions happen. We'll do that next. Okay. So our job is to quantify these different types of motions. To understand this, we're going to introduce a term, okay? We're going to introduce a term called as a degree of freedom. Which roughly translates, okay? Which roughly translates into the various ways in which or via which, okay, right? The various ways via which any type of molecular motion, we're talking about the translational, rotational and vibrational motions, okay, right? This is TR, ROT and VIB for short, okay, right? So the various ways via which a type of molecular motion could happen. So that is what is colloquially, referred to as the degree of freedom. Once again, we're not worried about the exact definition given in textbooks. We just want to understand that to quantify the different types of motions, right? We have what are called as degrees of freedom. And each type of motion, for example, translational motion, rotational motion, vibrational motion, etc., are associated with their own degrees of freedom. Okay. That said, so by the phrase degree of freedom, I refer to the various ways via which a type of molecular motion could happen. Okay. Now, I want to make it more precise. It's not just the various ways, it's the various independent ways. We'll very soon, while discussing some examples, I'll tell you what exactly the phrase independent means. Okay. Now, for example, consider any molecule. Consider any molecule composed of having n atoms. Okay, right? So you have like a molecular system comprising of n atoms. Well, n is greater than 1, of course, right? Yeah. Because if n equals 1, then it will just be an atomic system itself. And recall what we told about atomic systems. Atoms are subsets of molecules. We'll first finish the discussion on molecules and go back to atoms. Okay. So having any molecular system containing of n atoms. Now, just like we have a degree of freedom for the various types of motion, we can also have an overall degree of freedom for this molecular system having n atoms. So the total degrees of freedom, okay, right? The total degree of freedom, I'm going to call this degree of freedom total, okay, TOT, okay, D total is going to be 3n, where n is the number of atoms. Now this is intuitively easy to understand, right? If there are like n atoms overall, right, each atom can move along 3 directions, x, y, z, if we consider the Cartesian coordinates, or it can also change, to any other coordinate system. It can be r, theta, phi. It can be, it can be like, if you consider like the spherical coordinate system, it can be cylindrical coordinate system. It can be ellipsoidal coordinate system. It doesn't matter for our purpose. Okay. The point is, because we live in a 3-dimensional world, okay, right? We are living in space surrounding us, which is 3 dimensions. So, because overall, each atom in the molecule can move independently only along 3 different directions, 3 different perpendicular directions if we consider the Cartesian coordinate system, right? So the total degrees of freedom for the molecule, considering all types of motions, is going to be 3n, okay, right? Along x, y, and z, for example. If we consider, the Cartesian coordinate system, then the direction in which each atom can move is 3, right? Because it's a convenient system for us to consider along the Cartesian coordinate system, because along any other direction, they can always be expressed in terms of x, y, and z. When we consider their independent motion, it can only be along x, y, and z, because if it is moving along x, it is independent of its motion along y and z directions, right? Are we clear? Because these are the three independent variables. Okay, so overall, the total degrees of freedom of a molecule having n atoms is going to be 3n, right? Yeah. Now let's consider the translational degrees of freedom. I'm going to refer this by the symbol dTr. Okay, right? Now, well, it's kind of easy, right? If we consider, the translational degrees of freedom, what are the independent ways via which translational motion can happen? It's only 3, right? I'll write the 3 better, sorry. It's only 3, because the molecule can undergo motion along the x direction, y direction, or z direction, right? And notice that, see, because a molecule is a collection of atoms together, we cannot have one atom alone. One atom alone moving in one atom alone translating in one direction, and then the rest of the atoms, doing some other kind of translation motion. That is absurd, right? And that is why there is no end dependence here. Whereas for the total degrees of freedom, there is the dependence on the number of molecules. As far as the translational motion itself is concerned, there is no end dependence. Why is it? It is because the atoms are all bound together. You cannot simply, have one atom alone move in one direction without the rest of the molecule getting broken. Okay, right? Or in other words, without the chemical bonds getting broken, the one atom or two atoms cannot move on their own. That's why the translational motion has an independence from n. Okay, right? Whereas the total degrees of freedom has an end dependence, the translational degree of freedom has no end dependence. All the molecules have to either, go in one direction or the other, etc., etc. Are we good? Okay. Next, we shall be looking into the degrees of freedom corresponding to rotational motion. Okay. I'm going to call this d arrow t. Okay. Now, what is this d arrow t? Once again, right? Similar to your translational motion, there can be 3 independent axes, right? The x-axis, the y-axis, and the z-axis. They're all independent from one another, independent axes. So motion can correspond to any of these 3 directions. And once again, notice that there is no end dependence. There is no end dependence because when one atom alone, when one or two, when let's say a couple of atoms alone in a system rotates, okay, right? With the rest of the molecules staying intact, that situation would be impossible, because then they would lead to major deformities in the molecule, right? In the molecular arrangement, in the chemical bonding state, etc. So once again, there is no end dependence here. When we consider the rotational degrees of freedom, the entire, all of the molecules have to rotate. All right, yeah. So this is 3, considering all the 3 axes. Notice that for linear molecules alone, okay, right? For linear molecules alone, derotate, okay, right? I'll write it here. So this is for non-linear, a more general non-linear case. But for linear molecules, your degrees of freedom of rotation are only 2 and not 3. Please observe this point carefully, okay, right? Now, if you consider any linear molecule, right? What's an example of a linear molecule that comes to your mind? The simplest one is H2. 2 atoms has to be a line, right? Yeah. Or for example, you think of a slightly more complicated case, a triatomic carbon dioxide. That's also linear. Now, for all the linear molecules, again, you can define 3 perpendicular axes. But one of these axes will pass through the nuclei of all the 3 atoms, correct? Now, motion along that axis, right? That axis is actually going to be ignored, okay? Ignored for the purpose of considering the degree of freedom. I will tell you why it is. I will tell you why it is in a tutorial. So I haven't told you the reason yet, okay? I haven't told you the reason, but kindly notice that the rotational degrees of freedom for linear molecules is only 2, and it does not include the axis wherein all the nuclei lie. For example, if you consider H2 molecule, right, and let's say that this is the axis, indicated by my index finger, right? This is the axis in which the nuclei lie, right? The rotational motion about this axis is incredibly difficult at normal temperatures. Okay, right? Yeah. I will tell the reason why in tutorials. I haven't told you the reason, but the internuclear axis is ignored. So key pointers for linear molecules when considering rotational motion, purely rotational motion, that is, okay, right? The axis wherein the nuclei of the atoms lie, that is ignored. Okay, right? And notice that I haven't told you why. I haven't told you why yet. Of course, I'll tell the answer in the tutorial. So therefore, the total number of degrees of rotational freedom for a linear molecule is only 2. Are we clear? So in this class, we looked at the various types of motion, various possible types of motion that any molecule can undergo, and we started our discussion of the concept of degrees of freedom, and we have discussed the total degrees of freedom, which has an end dependence, and we discussed the translational degree of freedom and the rotational degree of freedom. And I told you that for linear molecules alone, rotation about the axis wherein the nuclei of the atoms lie, that has to be ignored. So we end this lecture on this note, and we shall continue with the next lecture. Thank you so much.